out a little bit, and then we will start going over them. All right. So this one that we have here is not as long as the one you'll see on your quiz. It's not they're not going to be as long, but this one is going to be really good because we have both types of quantifiers in there, so it's really good practice for what you will see on the quiz. So as I already mentioned, the first step is to always just write down negation of the entire statement that you have. I'm going to run out of space, aren't I? I am. And on your quiz, kind of like what happened with the truth table ones, you can kind of just use, the caret above the 6 for and, the letter V for or, you can create an arrow. I do include the backwards E and for A, so you can copy and paste that because there's not the function editor in the type of question that I put this in. But also, if you're having trouble with the backwards E and oh my gosh, and upside down A on the quiz, and you're just or you're just tired of copy and pasting it. If you put a regular E and a regular A, I'll accept it. But it should be the backwards E and the upside down A, and try to just keep copy and pasting that if you have the time. So remember, these all follow like a very common process. So the first thing is we're always going to use one of our negation rules. In this case, since we're bringing it inside of an existential, it's going to be an existential negation. And remember what that does is it brings the negation inside the quantifier. Everything else is going to stay the same for now. But then in the front, the quantifier changed to the other quantifier. And remember now the point is that we need to push this through. So at this point, since what we have is we have something and something else. Now that something else in the back is a big old blob of stuff, but that's okay. So since it's ultimately an and statement, we can use De Morgan's to push that. Whoops, and I'm being bad here. I'm writing the reasons, but not the steps. The first one was a step on line 1, and this will be De Morgan's on line 2. So De Morgan's tells us to bring the negation inside and negate each piece. And yes, I'm missing a thing in the middle. That's why there's a space. I'll get to it in just a second. And De Morgan's also says flip the sign. So at this point, let me erase this part real quick. What we have up to here is perfectly fine. Like, we don't need to do anything with that. That's going to stay the same for the rest of the problem. And we'll actually including that or as well. Oh, actually, that's going to change. So up to here, we don't have to deal with anything right now. So really what we're focusing on right now is this back piece, because now we have this negation in front of the for all. So you need to use another one of the negation rules again. And since it's a for all, that's going to be a universal negation. So we bring the negation inside and switch the quantifier. So from the first step to the second, the first symbol changed because of the existential negation. So yes, so existential negation and universal negation follow a very similar pattern. You bring the negation inside and you switch the quantifier. So that's why the quantifier switched. It's because that's essentially just what our negation rule tells us that, and I can't make that look good. There we go. So now at this point in the question, we're fine up to here for now. So now we need to take care of that negation in front of this implies, but we don't have a rule that tells us how to bring a negation inside of an implies. So we need to use our implication rule on line 4. So most of this stuff in the front stays perfectly the same. And what we need to change first is that implies. So the implication rule, scroll back up. Hello. There we go. The implication rule essentially negates the thing in the front, changes the implies to an or, but leaves the back piece. I should clean that up a little bit, ran out of space. So we're going to negate the first piece, so we're going to negate the q of x. Change the implies to an or, but then leave the r of x alone. That's what our implication rule tells us. Questions so far? I know you were supposed to have tried this on your own, but I know this one's a tricky one, so I want to go through it a little slow. So then we still need to be dealing with this negation here. We didn't do anything with it at that point because we couldn't. But now that we switched the logical connective to an or, we can go ahead and quote unquote distribute that through using De Morgan's. That'll be De Morgan's on line 5. All the stuff in the front isn't changing right now. But back here, we'll get a not, and yes, you do need to write that, q of x and a not r of x. And now we need to change the sign because we're using De Morgan, so it will become an and. Almost there. There's 2 last steps we need to take care of. One of them, so at this point, we've pushed the negation through all the way. There's no longer going to be any negations we need to push through because if you notice, all of the negations that are left are directly in front of just p of x, q of x, or r of x. They're not outside of something that has a connective in it. So what we do now is the one thing we need to deal with is there's a double negation by that q of x. So we're going to go ahead and get rid of that using our double negation rule, of course. Let me clean this up a little bit. I got rid of a parenthesis I need. So we're going to use our double negation rule on line 6 to change that double negation, essentially make it go away, if you will. I will say on the quiz, there are different types of questions you could see. Not everyone's going to necessarily have the same question, but I believe there is one type of the question where you would be using double negation twice. Like there's 2 things that you would need to use double negation on. You can just do that together in one step. So you can just say double negation on the above line and just change both of the things that had the double negation. Again, not everyone's going to need to do that. So don't think that you've done something wrong if you don't see 2 things with double negation. But I do believe one of the question types that could pop up has that. We're not done. We've got one last step. So the last step, so remember that the for all essentially links up to the implies and there exists links up to and. So what we have right now is we have this for all, but it's attached to an or. We do have the there exists attached to an and, so that one in the back is good to go. But what we need to do is we actually need to change this back to an implies. Maybe I should be careful with the word back. We need to change this into an implies because essentially because we need to match them up to their, we need to make them match. So what we're going to need to do is we're going to need to do an implication rule on line 7. So remember what an implication rule does is it's going to change the or to an implies. It's going to leave the back piece completely alone. Like that's not going to change at all. But it negates the front piece. Okay, so I lied. There's one more step because then we have to double negate that. Again, the ones on the quizzes, your quiz today, are not this long. I don't even have room for double negation. I ran out of space. You wouldn't do this, but because I ran out of space, I'm also going to get rid of this double negation in the front and leave it as that. Technically, that should be a completely separate step, but I ran out of space. The thing to take away from these types of questions is the first thing you're always going to write down is the given, which is just the negation of the thing that you're asked to negate. The second thing you're always going to do is either an existential or universal negation, depending on what the quantifier in the front is. If it's a universal quantifier, the upside down A, you're going to use universal negation. If it's an existential, the backwards E, you're going to use existential negation. Then depending on which quantifier you're starting with, you're either going to land on De Morgan's or implication. So those are the two big rules for this type of question is De Morgan's and implication. So you're going to have to use both of them. It just depends on which order you use them in, depending on which quantifier you started with. If you start with an existential, you're going to use De Morgan's and then implication. If you start with a universal, you have to start with implication and then use De Morgan's. And every once in a while, you get a double negation rule that pops in here or there. But for the most part, the main rules you're going to be using are the negation rules, De Morgan, and implication. Questions concerned on that?
Aaron, it's Vince speaking. Just where again can I just kind of find more of the stuff that's going to review the De Morgan's and implication stuff, but I guess in more relation to this predicate logic instead of seeing it as like the original. Excuse me.
So this, let's see where it is at in your book. Quantifiers, translation, negation. How far do we go here?
I guess what I'm seeing is, are asking it, are there like examples of seeing like, hey, this is De Morgan's explained with predicate predicate logic that I have like an example to look at, or do I need to go back to the previous sections and just look at that and then kind of apply those patterns we were talking about?
It's probably going to be more about jumping back to, so this came from 1.3. So there is a little bit more in your book. Well, maybe not. I haven't read exactly what goes on because my notes do follow your book a little bit. But on page 32 and 33 of your book, if you want to write that down, is where that starts. I don't know how much more. It doesn't look like it goes into a ton of detail at all. But 32, 33 is where it starts in your book. In terms of finding this like in a different location, like Google, and I just tried to do this the other day. Someone in my office, I tried to look up some questions. Trying to look up material for this class online can be complicated because the large majority of the time, everybody else does it in more detail than we do. Because this class goes very quickly because we have to cover about 2 semesters worth of stuff in one. So we touch on everything in a very kind of broad, let's talk about the basics and move on kind of way. And everybody else is like, yeah, let's talk about this in the full way. So a lot of the material you'll find online is too complicated.
That's fair. I'll just kind of use these examples on these pages, I guess.
Yeah, and look back at the 1.3 notes. If you want extra practice, like you would have to figure out the answers yourselves, so you could always just email me and say, hey, is this right? But with these, the nice thing is that you can kind of just write one out Like, I pulled this off the top of my head, and like, there's no real pattern I'm looking for here. It's just that if I write down a there exists, I need an and in there somewhere, and if I write down a for all, there needs to be an implies somewhere. But besides that, you can essentially write your problems yourself and just try to tackle it. And of course, email me if you want me to check it over. But that's also a thing. Why is the last double negation needed? Isn't the application rule just dropping the not in front of the P? Oh, wait. Yeah. So you could actually just do it that way. So both would be correct.
Aaron, I have a question.
Yeah.
All right, so I know this might sound a little stupid, but can you please explain to me how you got from the given to the exponential negation? Like, can you break that down a little bit more detail?
I can try. Let's see. So first off, let me pop back over here real quick and scroll up here. So the sassy answer is it's just a rule. But to reiterate what the rule is telling us now, of course, what we were just looking at has a lot more than just a p of x. But this p of x can be absolutely as gross, as long, as terrifying as we need. So whenever we want to negate one of these quantifier statements, we use one of these negation rules depending on which quantifier we're starting with. But the rule kind of stays the same. As what's happening is we're bringing the negation inside of the quantifier. So it's no longer outside of the quantifier, it's kind of next to the actual statement now. And then you change the quantifier. Now, if you think about it, if I said something like, now these statements are going to be stupid, but I'm just, that's not. So for all animals, X is a dog. So we'd have some for all X and maybe D of X because it's a dog. If you wanted to prove that false, which would be essentially what you're trying to do with the negation, you're trying to show that that's not, you're trying to go against that, then you would need to find an animal that is not a dog. You would have to find at least one animal, there exists, such that it isn't a dog. That's kind of, if it makes more sense to think of it that way about why the quantifier actually changes. If you want to essentially negate a for all statement, you then have to find one thing that made that false. Whereas if I say something like, there exists an animal that is not a dog, and you want to prove me false on that there doesn't exist an animal that's not a dog, you'd have to somehow show me that all animals are dogs. So that's why the negation of a there exists is a for all. So what we were doing over here in the warm-up is, since the first thing we have is a there exists, we're using our existential, and we're taking this negation, and we're bringing it inside, and we're changing the quantifier.
Okay, so is it reverse logic as well? So say, for example, it's a for all, we would have to negate it to, there exist.
Uh-huh.
Okay, that makes sense to me. I was like, oh, well, that's confusing. But I got it.
Okay, cool. So Brad, back to your question, why is the last double negation needed? Oh, so I was started to so Brad, you're actually right. I could just use a straight implication rule on that. I'm not wrong either. We would both be correct in doing that. So the thing is, with the implication rule, technically is stated like this. So if you want to say to me, well, it starts with a not P and then just becomes a regular P, you're correct. I'm also correct technically, because technically this could be written as not P implies Q. Like a regular P is the same as a not P. So going from not P to not P using the implication rule is also technically correct. Either or. But you were also correct. You could use the implication rule completely by itself and then not actually really need to call upon double negation. But if you didn't recognize that off the bat and brought in the negation, you're technically not wrong. Yeah. That's a good question. Any more questions on this guy? Okay. So, even or not. So, remember the definition of, oh, yes, I meant to say that already. So, of course, your exam's coming up next week on Thursday. There will be a review guide for it. It should be ready tomorrow, so keep your eye out on Blackboard for that. I don't know exactly when tomorrow it'll hit Blackboard. It might be a bit later in the day because I pretty much have the structure. I just need to go back and tweak some things. But it will be up on Blackboard tomorrow. There will be a brand new folder in the course content that says exams, and it'll have the exam review in there. And then I will be getting the answers to that up as soon as possible, but that might take another day or so. But yeah, thanks for reminding me about that. The exam will be given through Blackboard. It's going to have the same kind of setup as the quizzes. The only thing that's different is that the exams have the official time limit. So with the quizzes, you know, you can keep going after the time limit. Exams, you won't be able to. It'll just disappear, and whatever you don't get done is sad. The way I do exams, though, don't freak out until I finish my sentence. What I do with exams, so this is a 75-minute class. I have a process that I use that gives me a pretty decent estimation of how long it takes you to take an exam based off of how long I take to take the exam. So essentially, what most people use in the math department is I need to give you about 5 times the amount of time it takes me to take the exam. So I shoot to create approximately a 60-minute exam, which means that I would have to take the exam in about 10 to 12 minutes. And then you have 60 minutes. Well, sorry, I should be careful of my phrasing. That sets it up to be approximately a 60-minute exam. This is a 75-minute class, and I'm going to have the time limit listed as 85 minutes. So you'll have a little bit of extra time. If you're someone who has a class directly after this one, I will have it open a couple minutes early so that you can start it a little earlier. If you have a class directly after that you would need to leave for, so that you can still have that extra 10 minutes if you need it. But I try my very best to write the exam to be approximately only a 60-minute exam for the quote-unquote average student, whatever that means. So a 60-minute exam for a 75-minute class. Restrictions on the exam. So you can use your notes because I can't. People are going to use them even if I say you can't. So it's OpenNote. Technically open resource, but you're not really going to find many other resources that are helpful besides your notes. And the only, you can't talk to other people about it. You can ask me questions, but you can't talk to fellow classmates about it. You can't help each other out. You can't go on Chegg and post the questions to get answers. That's bad. Essentially, anything that would be you asking someone to solve it for you is not good. But you can use your notes. You can ask me questions. You just can't talk to each other. You can't talk to internet strangers. So on and so forth. Besides that, there's no restrictions. You don't need a lockdown browser or anything like that. How many questions will be on it? That depends. Usually the 75-minute class. Usually there's not more than 20 max. Some of them might have tiny little parts to them, like this question in the warm-up right here would be considered one question, even though it has 2 parts. Usually my exams land around 15 to 20 questions. Do we get on Teams to take it? I've decided on no on that. You don't have to be on Teams to take it. If you want to come and chill on Teams so that you can easily ask me questions, because I will be here. I'll be just sitting around twiddling my thumbs. But I'll be here in the Teams call on the exam day. If you have questions, feel free to stop by, or if for some reason you just want to sit here in the Teams chat while you're taking it, you can do that too. Will this all be typed out just in case? You mean all the stuff I'm rambling about? I could like write it up in the review. I could post it when I post the review. Can you give optional homework that covers material on the exam? I could. Well, see, I would say yes, but all of the questions on web work I've essentially already assigned. So you would just be seeing the same questions again. I mean, I can maybe there's a couple that I didn't put on there. I can check and I could put one up. It just might be a couple questions that you've already seen before because web work does not web work. Web assign does not have a very large bank of questions for this class. But my review guide is what I suggest to do over WebAssign stuff. Like I'll try to create a WebAssign thing. I can try to do that. No problem. But the stuff I put on the review guide and the questions I put on the review guide are highly suggested to do. And then of course you'll have the answers. It might take me a day or two to get them up, but you'll have the answers. Because I write the review guide and I write the exams. WebAssign does not write your exams. So something written by me is probably better practice than something written by WebAssign, but I can totally try to do that. Anyway, any more questions about that before we continue on with this thing? We're not gonna have time to do notes. And we can also talk about it again on Tuesday, because again, I'm hoping to take a little bit of a Tuesday as a review session. All right, anyway, back to the warm-up. So show that this thing is even and then the other thing is odd. So remember the definition of an even integer is that it can be written as some 2k, some 2, the variable doesn't matter. So essentially what we want to do is we want to find some way to be able to take 16z plus 20 and write it as 2 times something. Now since both of those numbers are even, they're divisible by 2, so you can factor a 2 out, leaving 8z plus 10, and that's the answer. Well, if you type this into Blackboard, it should hopefully accept it because I put that format in the key. Or if you just put this side, that's also perfectly acceptable as well. That side is technically more of what I'm looking for, the 2 times 8z plus 10. Now, if you're math savvy, you might say, okay, well, I could also factor out a 4. I don't care. So an even number is not defined to be 4 times something, it's defined to be 2 times something. So I don't care if I could pull out more from it, I just want to pull out the 2. So this is even because I can write it as 2 times 8z plus 10. Questions, concerns about that? Now, odd takes a tiny bit more brain power because of that extra plus 1 at the back. So what we want to do is we want to take this 4m plus 17. Now notice that I could rewrite this as plus 16 plus 1. And then I essentially have this set up for my plus 1 in the back. So what I want to try to do is once I pull out that plus 1, I want to essentially forget about that for a second and try to take the rest of it and make it look like some 2 times something, which we can do. So I'll write it out like this because I wrote the other one like it. Is we could pull out a 2 from that 2m plus 16, leaving 2m plus 8. And then the plus 1 just stays at the back. And now that I was able to algebraically manipulate 4m plus 17 into some 2 times something plus 1, that means it's odd. So again, you could write this entire piece in as your answer, or you can just write this right side. Well, that's what, yeah, we just went from this really scary logic thing to this, oh, it's even, yay. Questions, concerns on the even odd question? That's it. That's all you have to do on the quiz for those. Is just be able to find what you can write it as in terms of 2 times something or 2 times something plus 1. Now, counterexample. If p is prime, then 2p plus 1 is prime. And I realized after I wrote this that this was one of the questions on the quiz, so I had to go change that. So remember, if we want to negate a implication, then we essentially want the first piece to be true, but the back piece to be false. So you want to take a prime number such that 2 times that prime number plus 1 is not prime. Now, if you were to just start, listing primes here, if we use 2, we get 5, which is prime, so that's not our counterexample. If we use 3, we get 7, which is prime. That's not a counterexample. If we use 5, we get 11, which is prime, so that's not our counterexample. If we use 7, we get 15, which is not prime because it's divisible by 3 and 5. So a counterexample is 7. What are some other counterexamples? So let's see. I think 21 is, sorry, that's not 21. 11 would not be a counterexample because you get 23, and I believe 23 is prime. 13, I do believe, is a counterexample because that gets you 27. Good. So 11 is a counterexample. 15 would get you 31, which I believe is prime. 17 is a counterexample because it gives you 35. 16 wouldn't be because 16 is not prime. So remember, we've got to start with a prime number. You're good. That happens a lot. People just pick any random number, and so I actually do want to draw attention to that. We got to make sure that we start with a prime number and end with not. These are very easy to overthink.
So we're just simply plugging in for P a prime number, and then we plus it by 1, and we try to get a number that is not prime at the end.
Right, because we're trying to make that thing false, which would mean that the 2p plus 1 has to not be prime.
And we just go in ascending order?
I mean, you don't have to use the, you don't have, my brain stopped working. You don't have to go from the smallest and keep counting up and up and up and up until you find what that works. You can also just do trial and error. Like if you wanted to just pick 11 first off, or you wanted to just try 7 first, or you wanted to try 13 first, or you technically can do it however you want. You can just pick a bunch of numbers and find one that works.
So how many counterexamples are you looking for in this type of question?
Oh, just one. Just one.
Gotcha. Okay.
I just wanted to give a couple ones for the warm-up purposes in case people found other ones. 13. I don't think so. I think I checked that one. Let me see. 2 times 13. Excuse you, calculator. My calculator's angry because its battery is low. So 13 won't be a counterexample because if we find this, we'll get 27. And 27 is divisible by 3. So it's not prime. So 13 is prime, but 27 is... No, wait. We wanted a not prime. I'm sorry. So yeah, 13 works. We wanted something that wasn't prime. Yeah, no, I'm sorry. Whew. I confused myself. 13 does in fact work. Because the point is we wanted a non-prime number. Sorry about that. All right, questions, concerns? All right, we've got a hot second worth of notes. Notes is what I was trying to say there. Yes, for counterexample questions, you only need one. I was just trying to give a bunch in case people found different ones, but you just need one.
How would 17 work?
17. Did I get stupid on that too?
I believe 35 is divisible by 5.
2 times 17 plus 1 is 35, which is divisible by 5. So remember, it's sometimes hard to keep track. We want the 2p plus 1 is prime to be false. So we want it to create a not prime number. So since 35 is divisible by 5.
Would there be a case where you would swap the statement or just negate it where it is like, or is it always a prime? So the statement will always start with if p is a prime, then so on and so forth.
No, I was almost going to say on your quiz, yes, but actually I threw one in there that not everyone will see, but some people will see that says for all real numbers, something. So it can depend. It might not always be prime, but whatever that first statement is, no matter what that statement is, that's what you're taking to be true. So if it says for all real numbers, then you just take any number. If it says for integers, you just take integers. And then that back piece is the thing that you want to try to make false. Does that make sense?
Okay, so the back piece can be either the prime or the not prime one. Maybe I'm not making sense of it, but I'll try and figure it out.
So I could also say, counterexamples are ones that I should not pull off the top of my head. No, this is technically true, so this wouldn't have a counterexample. No, wait. Yeah, no. Yeah. Wait. My brain. Ooh, that does have a counterexample. Brain. Yeah, so actually, hold on, this is actually a decent one. So counterexample questions are not something that I should create off the top of my head, so I wasn't expecting this to work out. Exactly. So we would want a real number, but we would want when we square it for that thing to not be greater than the original. And in this case, a counterexample would be something like 1/2, because 1/2 squared is 1/4, and 1/4 is not greater than 1/2. So it doesn't have to deal with just primes. It can deal with any type of number, and it's just based off of this statement. If it's the if thing, you want to be true, and then the piece behind it you want to be false, no matter what those things are. And I believe you are correct. Correct. Actually, no, decimals greater than 1 wouldn't work, but any decimal less than 1 is going to be a counterexample, Arpon. Sometimes I say the word decimal meaning something less than 1 and then forget that there are decimals greater than 1. All right. Any more questions on the warm-up? Alrighty, so let's jump over to our 1.5 notes for a little bit. Don't have too much time, and that's unfortunate, which means we'll be taking a little bit of time on Tuesday to get through more of these. So remember, we started talking about proofs, and we started talking about a direct proof, which is just essentially taking statements and just following from the statement before. And so we did one by hand from scratch. A lot of what you'll see on your homework is something more like this, where you just have to fill in the blanks. So I want to try one of those. So what we want to do is we want to prove that if a and b are odd integers, then a times b is also an odd integer. So what I would like to do first is I'd like to come over to the side, and I want to do that scratch work because that's probably going to help us fill out the things. Because if you're looking at, especially with the homework and the blanks are all over the place and it's really scary looking, I think coming off to the side and trying to do the scratch work yourself can help you then jump back in and put things where they need to be. So if a and b are odd, we're going to use the definition of odd to say that they can be written as some 2k plus 1 and 2k, well, 2k sub 1 plus 1, and then 2k sub 2 plus 1. So remember, that's just the definition of odd. And then let me take a look at what a times b would look like then. So I'd have 2k sub 1 plus 1, 2k sub 2 plus 1. And then hopefully your algebra is up to snuff. because we're going to FOIL that, first, outer, inner, last, like essentially distribute both terms. So we would get 4k sub 1 k sub 2 plus 2k sub 1 plus 2k sub 2 plus 1. Now we want to show that that's odd. Now odd always needs a plus 1 at the back. Well, hey, we've got a plus 1 at the back, so let's not touch it. Can we somehow create the rest of it to look as 2 times something and then leave that plus 1 alone? Well, everything in front of that plus 1 is divisible by 2, so we could pull that 2 out, which would leave us as, I'm going to run out of space, 2k sub 1, 2k sub 2, plus k sub 1, plus k sub 2. And that's essentially the scratch work for the proof, because now we've just shown that a times b is odd, because we were able to write it as 2 times something plus 1. So let's hop back to this thing and try to fill out these blanks. So remember, to start off a proof, you always essentially state what you're given. So we are always given an if statement that we're assuming to be true. So we're going to let a and b be odd integers. That's what we're allowing them to be. And then remember, the next thing is we always want to say what we want to show, what we want to prove. So we want to show that a times b is an odd integer. So again, usually we don't write the steps out, but if you're looking back at the process that we wrote down the other day, our steps would flow out like this. So then our third step is to essentially show them the proof, which is essentially this scratch work on the side that we just did. So since a and b are odd integers, there exists integers k sub 1 and k sub 2, such that a equals 2k sub 1 plus 1, and b equals 2k sub 2 plus 1. And then we're essentially just going to recreate our scratch work. So we found that when we multiplied them together, we replaced the things with what they were equal to. We FOILed it out. Does anyone need a FOIL reminder?
Please.
Okay. Let me just finish writing this out and then I'll do one. And so then we were able to factor the 2 out of those first 3 terms. But we left the plus 1 at the back alone. Ooh, I froze. Oh, my laptop's angry. One moment, please. There it is. Let me make my 2's match. I always jump back and forth on how I write my 2's. So that was essentially our scratch work. Now remember, axiom 1 was the thing I told us we're going to call on upon a lot, which is the thing that tells us when we add or multiply things, integers together, we still get integers. So the thing we need is we need to essentially say that this thing that's inside of the, I circled the 2. The thing inside of the parentheses is an integer. So what we're going to do is we're going to break it up into its kind of 2 pieces. We're going to say 2k sub 1, k sub 2, and the k sub 1, sorry, nope. So well, let me write it out and then I'll explain. Having trouble talking and writing at the same time. So the reason I have to split it up like that is this reason. We already know that k sub 1 and k sub 2 are integers. So that plus k sub 1 and plus k sub 2 at the back, like we don't need to care about those separate pieces because we already know that those are integers because that's how they were defined. That 2k sub 1, 2k sub 1, k sub 2 in the front, we would need to explain as an integer because we created that out of the pieces. But since axiom 1 gets us that when we multiply integers together, it's an integer, that'll be fine. And then the last piece is essentially, since all of those 3 pieces of the sum are integers, we can say their entire sum is an integer by axiom 1 as well. So essentially, you always need to reiterate to them the fact that the pieces of the thing inside of the parentheses are integers by axiom 1. So therefore, a times b is an integer. So leave that up for a couple seconds, then I will pop over, we'll do a quick FOIL review lesson, and then we'll be out of time and you'll have to take your quiz. So we did not really get anywhere, but it'll be all right. Also, questions, concerns about that proof setup before we jump over to the FOIL little review session.
Could you explain the sub-K for it? I'm still a little confused on that.
I'm sorry, the what?
Like the sub-K, like
Oh.
sub-K. Yeah.
So the reason we need that is because we can't assume that they're the same number. Like, since 5 would be 2 times 3 plus 1, but if we wanted to then use 10 as our even number, that would be 2 times 5. So like we can't just say that A is 2k plus 1 and B is 2k plus 1 because they're not necessarily going to be the same number. So we need some way to differentiate between the two. So we usually use subscripts. Now, if you were doing this by scratch on like by yourself, could you do something like what? This? Yes. The reason I use the case of 1 and case of 2 is because that's what your homework is expecting and it will not take anything else. In general, could you just use a different letter? Yes. But we just need some way to differentiate between the two things because they might not be the same number. So we just use subscripts because that's usually what people default to, and that's also what your homework's going to expect. I believe on your homework, if you just use an underscore, that's what's going to accept that on your homework. Yeah. All right, so little FOIL lesson. Let me do just generic things first. Well, let me do no, let me super generic. It's called FOIL because it means first, outer, inner, last, and it's essentially just a distribution technique when you have more than one thing to distribute. So essentially, and there's a couple ways you could do this. You don't have to use the actual FOIL method if you just want to distribute it separately. But essentially what it means is you take the first things in each, parenthesis and you multiply those together. So that would give us A times C. And that's where we got the 4 case of 1, case of 2 from and the one that we were working on. So I'll also link this to the thing we were actually doing as well. And then you take the outer. So we take the outermost values and multiply them together. That's what gave us our 2k sub 1, because 2k sub 1 times 1 is just 2k sub 1. Then you take your inner, which are your innermost values, which will get you b times c, which got us our 1 times 2k sub 2. And then you take, what other type of line can I use? I'm going to use a spiky line. You take your outer numbers and multiply them together. Whoops. And that's what gave us our 1 times 1 is 1. Essentially, as long as you multiply every pair of things together, it doesn't really matter what order, but FOIL is kind of an agreed upon, most people use it type of setup. But as long as you're multiplying all of the pairs of things together, then you're fine. But that's just like a way to help make sure that you covered everything. So that's what FOIL is. First, outer, inner, last. All right, so we did one question worth of notes. It's time for your quiz now. So it should be on Blackboard already. And remember that the time limit is not official, so if you take more than the 20 minutes, just hit the cancel button on the scary box that pops up. If you really don't want to copy and paste that backwards E and upside down A, you can use the regular letters. I probably should make you copy and paste, but if it's not worth your time, don't worry about it for the quiz. And I'm going to stop talking now.